Hi everyone and welcome to the lab number 13. This lab is about polarization and refractive index. Off the bat, this lab will be some sort of continuation of the two previous lab. We'll have a lens involved and we will also have refraction involved. And then before we will fully go into polarization. And so for the lens and refraction part of it, we will have to deal with what we call an optical bench. You will have a light source producing light rays that will go through a lens and will be refracted in order to create an image on the screen. So this is what, in general, the optical bench looks like. So you have your object here. The arrow is my object. Somewhere along that object, I have my lens. Okay. This is obviously a concave lens, a biconvex lens, which is by definition a convergent lens. That is, when rays go through that lens, they are forced to converge to one spot. And a couple of things about the lens. So if you have a light ray that goes straight towards a convergent lens, let's say a light ray like the tip, when it reaches the center of your lens, it is converged, it is refracted, it's bent, and in that process of refraction, it goes through a point we are going to call F. All right? That's the focal point. So if you have an object and a ray goes from that object, when the ray goes through the lens, it is refracted and sent through the focal point of our system. The focal point is the point where you get the best image. All right? Now, the question is, what if a ray is not coming in a parallel way? Okay. Here's another scenario. Let me try to extend this lens a little bit. Let me make it having two equal hemispheres. That's what I'm trying here. So in the case the light ray leaving the object goes through the center of the lens, which is also called the center of curvature, that ray goes unaffected. All right? It goes straight through. If the light ray that is not going parallel, so if we have a third light ray that is not going parallel and it's not going through the center of curvature, but is instead going through the focal point on this side. So on every lens you have two focal points. You have one to the left and one to the right of the lens, and they're usually equidistant from the center of your lens. So if the ray goes to the focal point that is located before the lens, it gets refracted. When it reaches the center of the lens, it gets refracted into a parallel ray. All right? So usually we give names to these rays. The ray that goes to the focal point is called the focal ray. The ray that goes through the center of curvature is called the central ray. And the ray that is parallel to the surface on which the object sits is called the central ray. And the focal points before and after the lens that are equidistant from the center of the point of the lens, these focal points are the spots where you get the best image. It's just like for those of us who wear lenses, usually there's a distance at which you get a best image. That distance is called the focal point of your lens. Okay, even with the human eye, there are moments when at a certain point we cannot distinguish objects, but the closer we get, we can get a better view of those of the object, and that point is the focal point. Focal points are very much analogous to harmonics. Remember when we did the sound waves in the first lab, we had the first fundamental, we had the first harmonics, and so on. There were multiples of the fundamental frequency. Focal points are like harmonics. So if an object forms at a distance f from the center, if an image, a good image forms at the distance f from the center of the lens, I will also get a good image at a distance 2f, 3f, 4f from the center of the lens, okay? So this is a general idea of how lenses work. So you have, if a ray is parallel, it gets converged when it goes through a convergent lens. If a ray is a central ray, it goes undisturbed. If a ray is a focal ray, that is, it goes through the focal point, it is transformed into a parallel ray. And because these rays began at the tip of the arrow, what happens here is your tip of your arrow appears here now. Remember, these rays all began from the tip of the arrow here. And so when they converge here, what the observer sees, we have an observer here. What the observer sees, where the rays now meet, is the tip of the arrow. So the image has been inverted. And usually you can say an image is inverted or upright. Those are the two possibilities. So you have inverted or upright, but in this case, our image is inverted. You can have, our image looks bigger than the object, right? So we'll see the image is magnified. But usually the question you ask yourself is the image diminished or magnified before you answer? Some books, instead of using diminished, they say reduced. So is the image diminished or magnified? In that case, the image is magnified. And the next thing is, our image is real. The question is usually, is the image real or virtual? I'll explain that. The question is the image real or virtual? In that case, the image is real, okay? Why do I say the image is real? Because the image is formed by the rays themselves. And usually that image formed by the rays themselves can be captured on the screen. When we'll conduct the experiment, you will see that the image we'll create can be captured on the screen because the rays are real. When the rays are not real, you cannot capture the image on the screen, all right? I can go on and on talking about that and how, you know, Polaroids or olden days cameras are really good at creating images on films or screens when they deal with real images and all that stuff, but we don't have enough time for me to drag you into that. So just keep in mind that there are three types of rays involved in the formation of an image. The ray can be parallel, the ray can go to the center of curvature, or the ray can go to the focal point. And depending on where the ray goes, it determines what happens to the ray when it goes out of the lens. If the ray goes into the lens parallel to this axis, it is bent towards the focal point, towards and through the focal point. If the ray goes through the center of curvature, it goes undisturbed. If the ray goes through the focal point before the lens, it is bent parallel to the axis, all right? And in case the image was formed at the focal point, then we have a focus, and that is we have the best possible image. And an image is described by three properties. The image can be inverted or upright. That has to do with the posture of the image. The image can be reduced or magnified. That has to do with the size of the image. And the image can be real or virtual. That has to do with the what term would we use here to describe the authenticity of the image. Now I know we don't only deal with convergent lenses. We have divergent lenses. I don't know if I should show you an example of a divergent lens. Let me just do it anyway. Let me give you an example of a divergent lens, then we go into the lecture for today. So let's suppose instead of a convergent lens, our green eye observer there has a divergent lens. Alright? Okay, that lens is a little bit higher than the position of our observer. So let's put the lens here. Here's the central axis. I put my object here. I have my parallel ray that comes here. And when it reaches the center of my divergent lens, it is refracted. But remember, this is a divergent lens, so it is diverged. It is bent away from the central axis in such a way that if I extrapolate that bent ray, it will land on the focal point before the lens. So a parallel ray comes, it is bent. Let me make this look a little bit more acceptable. It is bent away from the central axis, and when you extrapolate it, it lands on the focal point. A ray going through the focal point will go undisturbed, right? And a ray going through the focal point will be made parallel when it steps out of the lens, all right? And a ray going through the center of curvature will go undisturbed, all right? What is the net result here? Here's what happens. This ray that went through the focal point and came out parallel is extrapolated as well, backwards. The ray that went through, that came parallel and that was bent away from the normal has been extrapolated. So here is where they meet. The central ray that went through the center of curvature, nothing happened to it. So, boo, big deal. Nothing really happened to it. So we cannot really use it to create the ray. But what we can do here though is, look at this. These two rays that have been extrapolated are formed here to produce the tip of an object. So this is the object, then the image is here. The image is formed behind the lens, in front of the lens, in front of the lens, not close to the observer eyes. In the convergent lens case, it was close to the observer eyes. In the divergent lens, it's formed elsewhere. All right. Let me take out the central ray since it brings nothing to a setup here. So our image is formed here, and as you can see, that image is inverted. It is diminished, and it's virtual. It's virtual because it's not produced by the rays. It's actually produced by the extrapolation of the rays. Okay, so that's it for the divergent lens. About today's lab, here's what we actually do. We will not always draw fancy stuff for experiments. Today's lab is a central axis. We have our object standing here. We have our lens here. We represent the lens with a straight line. And what we will see is that a light ray will come out there and go that way, right? That's the parallel ray. Then we'll have the central. Now I expect this to be state of the art, right? I'm not using anything fancy to be able to claim that I have the best drawing here, but I'm just trying to. That was the central ray. Then we'll have the focal ray. That's my focal ray. So let me use different color codes to make things easier. My object is purple here. All right. Here's my parallel ray. Here's my central ray, and here's my focal ray. All three rays meet here to produce my object. And as you can see, my object is enlarged, inverted, and real. But what really matters to me is, how do I know the value of this focal point. I just know it is a focal point, but how do I know what value it is? Like, if I give you a lens, I need to tell you what the focal point of that lens is. In order to find the focal distance or to know the position of the focal point, what we do in our experiment is we will keep moving this lens back and forth until the image forms, until the image that is formed is the best, until we have an image, a clear image formed on our screen. Our screen here, in our experiment, our screen will be a piece of paper. Our screen here is considered to be the observer eyes, right? Or at least this surface here, this is where our screen is, where we see the image formed. In order to find the focal point, a couple of things. You need to find what is the distance from the object to the lens. Let me use another color. Let me use red. So the distance from my object to the lens, I'm going to call that O. And then what about the distance of my image from the lens? I call that I, okay? So O is the distance of the image of the object from the lens, and I is the distance of the image from the lens. So in order to find F is the focal point. In order to find the focal point for which this distance is baptized the focal distance. So the distance of the focal point from the lens is called the focal distance. In order to find the focal point, here's the formula I use. The reciprocal of the focal distance is the reciprocal of the object distance plus the reciprocal of the image distance. All right? What that means is my focal distance can be obtained by multiplying image and object distance and then dividing it by the sum of image and object distance. These two formulas are what matter, right? And when we conduct the experiment, I will provide you with those values. There will be a meter stick, and I will clearly tell you, remember the uncertainty of the meter stick is 1 millimeter. And the experiment will tell you, hey, the object distance is this, the image distance is this. Go ahead and find the focal distance as well as the uncertainty of the focal distance.